In this video, we will go over thermocouples. Let's do one more review of temperature sensor characteristics. An ideal temperature sensor is accurate, repeatable, low in cost, easy to calibrate, and has a fast response time over a wide temperature range. Furthermore, a simple relationship between sensor output and temperature is highly desirable. As you watch this video, think about the advantages and disadvantages of thermocouples in terms of these characteristics. So, what is a thermocouple? A thermocouple is simply a two-terminal element consisting of two dissimilar metal wires joined at the end. Thermocouples work because of the Seebeck effect. In this phenomenon, a circuit made from two dissimilar metals with junctions at different temperatures produces a voltage. Let's go into this definition step by step. First, the two metals have to be dissimilar. For example, some thermocouples can consist of one nickel-chromium alloy wire and a copper-nickel alloy wire. These wires are twisted together on one end. When working with thermocouples, it is important that you twist the wires together. When you're in the lab, do not solder the wires together, since this introduces a third material that will affect your measurements. A voltage is produced when the junctions of the wires are at different temperatures. The twisted end of the thermocouple will be used to probe the environment of interest. For example, if you are interested in measuring the temperature of a candle flame, then the twisted end will be the one to place in the vicinity of the flame. The twisted end is called the hot junction of the thermocouple. The other end is called the reference junction of the thermocouple. Therefore, a circuit made from two dissimilar metals with junctions at different temperatures produces a voltage. At this point in time, it is worth noting that the relationship between temperature difference between the hot and cold junctions and the voltage produced varies with the materials used for the wires. Here we are discussing wires made of nickel-chromium alloy and copper-nickel alloy. However, other thermocouples use metals and alloys such as iron and constantan, or platinum and rhodium. Thus, depending on the application, thermocouples can be relatively inexpensive or really expensive. Now, the voltage difference of the two dissimilar metals can then be measured and related to the corresponding temperature gradient. The equation that relates this voltage to the temperature gradient is shown here. In this equation, S is the Seebeck coefficient. Now, this equation looks really simple, and I wish I could tell you that it's really simple. However, it is not. The equation shown here looks linear, but thermocouple output voltages are highly nonlinear. This is because the Seebeck coefficient S can vary by a factor of 3 or more over the operating temperature range of the thermocouples. The plot shown here demonstrates the nonlinearity of the Seebeck coefficient. Note that the letters indicate the type of thermocouple, such as type K or type E. Because of this nonlinearity, tables or equations are needed to convert measured voltages to temperatures, and vice versa. For a type E thermocouple, you will need the equation and table shown here to convert temperature to thermoelectric voltage. What is worth noting is that you will need 10 coefficients to convert temperatures between 0 and 1000 degrees Celsius to thermoelectric voltage. You will also need 3 more coefficients at sub-zero temperatures. Converting thermoelectric voltage to temperature requires a smaller number of coefficients, but you will still need 9 coefficients if you are measuring the temperature of an environment that is above 0 degrees Celsius. When working with a thermocouple, it is essential that you find these equations and coefficients, or a lookup table, in the thermocouple's datasheet. In the next video, you will see how you will be needing both of these equations in cold junction compensation. Thermocouples are a lot less straightforward to use than a thermistor or a silicon sensor. One of the biggest mistakes that you can make when using thermocouples to measure temperature is to connect a measurement system directly to the reference junction of the thermocouple. This is because the voltage measured by your system is proportional to the temperature difference between the hot junction and the reference junction where the voltage is being measured. Therefore, to determine the absolute temperature at the hot junction, you need to know the temperature at the reference junction. Now, how can we determine the temperature at the reference junction? This is a challenge that you don't encounter with integrated silicon linear sensors or thermistors. There are two ways to determine the temperature at the reference junction. So, to summarize what we've discussed so far, thermocouples measure the voltage difference between 2 points, the hot junction and the reference junction. To know the absolute temperature at the hot junction, the temperature at the reference junction must be known. One way to do this is to fix the temperature at the reference junction. You can do this by immersing the reference junction into an ice bath, which fixes the temperature at the reference junction to 0 degrees Celsius. Data sheets for widely used thermocouples include National Institute of Standards and Technology thermocouple reference tables. These are generated with the reference temperature at 0 degrees Celsius. The thermocouple voltage at this reference temperature can therefore be found in its data sheet. So, we know the voltage at the reference temperature is provided in the data sheet of the thermocouple. We now know this value if we look it up on the data sheet. Using a voltage measurement device, such as a multimeter or an oscilloscope, we can obtain a measured voltage. This measured voltage is actually the difference between the voltage at the hot junction and the voltage at the reference junction. We can rearrange this equation to show that the voltage at the hot junction is actually the sum of the measured voltage and the voltage at the reference junction. This is a very important equation because this enables us to obtain the voltage at the hot junction. And if we know the voltage at the hot junction, and if we know the voltage-temperature relationship of our thermocouple, then we could determine the temperature at the hot junction. Let's go over an example that demonstrates the use of the ice bath method to determine the temperature at the hot junction. Imagine that you have the experimental setup shown here, and you would like to know the temperature in the unknown region shown. Your measured voltage is 1.78 millivolts. If you use the ice bath method to fix the temperature of the reference junction to 0 degrees Celsius, what is the temperature of this unknown region at the hot junction? Here is a lookup table for the type T thermocouple that is used in this experiment. The first task is to find the thermoelectric voltage of this thermocouple at 0 degrees Celsius. To use the lookup table, we first find the row corresponding to 0 degrees Celsius. The number of the top of each column corresponds to the number of degrees Celsius to add to the corresponding temperature of the row. For example, if the bath were not an ice bath, and instead it were 3 degrees Celsius, we would pick the value at the intersection of the 0 degrees Celsius row and the 3 degrees Celsius column. Thus, if the reference junction were fixed at 3 degrees Celsius, then V sub T ref would be 0.117 millivolts. For this example problem, the reference junction is at 0 degrees Celsius, so we pick the value at the intersection of the 0 degrees Celsius row and the 0 degrees Celsius column. Therefore, at 0 degrees Celsius, the reference junction voltage is 0 millivolts. Now that we know both the reference junction voltage and the measured voltage, we can add the two together to get the voltage at the hot junction, which is 1.780 millivolts. 1.78 millivolts is located here on the table. This value is located in the row corresponding to 40 degrees Celsius, and in the column corresponding to 4 degrees Celsius. Therefore, 40 degrees Celsius plus 4 degrees Celsius is 44 degrees Celsius. This is the temperature at the hot junction, and this is how you use a lookup table to determine temperatures at the reference and hot junctions of a thermocouple. Here is a summary of the temperature sensors that we have discussed thus far. Out of the 3 sensors that we have discussed, thermocouples have the widest operating temperature range and have the fastest response time. No excitation is required for thermocouples because of the Seebeck effect, and the output of a thermocouple is a voltage. However, thermocouples have a nonlinear output that requires a higher order polynomial than the thermistor. Furthermore, thermistors are more accurate than thermocouples. This table highlights the pros and cons of the temperature sensors that you will have available to you in your final project, and it will enable you to select the best temperature sensor for your application. Now let's take a quiz. A lookup table for a type E thermocouple is shown here. Suppose you measure a voltage of 4.054 millivolts. However, your reference junction is no longer an ice bath, and the fluid in the bath is actually at 8 degrees Celsius, according to a NIST certified thermometer. What is the temperature of the hot junction? Please pause the video and use the equation and information shown in this slide to select the correct answer from the available choices. Then unpause the video to see the solution. The answer is 73 degrees Celsius. We know the measured voltage, which is 4.054 millivolts. We know that the reference junction is at 8 degrees Celsius. Therefore, we find the row corresponding to 0 degrees Celsius and the column corresponding to 8 degrees Celsius. The intersection of the row and column shows that the voltage at the reference junction is 0.472 millivolts. The sum of the measured voltage and the voltage at the reference junction is therefore 4.526 millivolts. This value is located in the row corresponding to 70 degrees Celsius and the column corresponding to 3 degrees Celsius. The temperature at the hot junction is therefore 73 degrees Celsius.